So we're going to discuss numerical integration in this section, and numerical integration is going to require us to try and find the area underneath the curve, but it's for functions that don't have an antiderivative. There's a lot of simple functions that just don't have antiderivatives, and here's just a few. Nonetheless, we're still going to need to find areas underneath the curve in certain circumstances. So how do you do it if we can't use the fundamental theorem of calculus, that is, find an antiderivative? Well, we're going to approximate things. We're going to draw in one case, we're going to draw in trapezoids in a bunch of subintervals and then try and calculate the area of all these trapezoids. Obviously, this is going to lead to something called the trapezoid rule. So how does that look? Well, if you divide up your interval a to b into equally spaced subintervals, then you can calculate the area of a trapezoid. That's a well-known formula. It's the height over 2 times the average width. So, okay, let's see. I didn't quite get that right. It's the average height times the width, which is what we have here. If you put this together for all these subintervals, then you can manipulate things and clean up the formula. You get a pretty decent formula, and that's actually on your handout. So the general formula is that you take the length of the interval, b minus a, divided by twice the number of subintervals times this expression. Now there's a little pattern in this expression. It's going to be the endpoints evaluated once plus twice the value of the function in the middle of all these function points in the middle. So we're going to do this for a very simple case, problem number 6, where we're going to integrate something which we could actually do in other ways, but it's just to give you a flavor of what's going on with numerical integration. So let's cut out of here and come back to here. Okay, so here's our integral. This is number 6. We're going to integrate from 0 to 8, the cube root of x dx. We're also going to calculate the relative percent error. Now, per the problem, we're going to use n equals 8 subintervals. So let's understand that a little bit. We've got the interval from 0 to 8, so 1, 2, 3, 4, 5, 6, 7, 8. Those are our subintervals. But keep an eye on something here. Even though we have 8 intervals, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 endpoints associated with these 8 subintervals. So there's always going to be one more endpoint than we have subintervals. Nonetheless, n in this case equals 8. So how does the trapezoid rule look in this case? Well, let's first of all figure out b and a. b and a come from the limits of your integral. So in the case of problem number 6, this area is going to be approximately 8 minus 0 over 2 times n. Coincidentally, what's n equal to in this particular case? It's also 8, although it's a different 8 than this one. This is the upper limit of our interval, times f of 0. That's this endpoint, plus 2 times f of 1, plus 2 times f of 2, plus 2 times f of 3, all the way up to f of 7. 2 times f of 7 plus f of 8. Let's see if we can't clean that up a little bit. Out front, this reduces to 1/2. F of 0 is going to be the cube root of 0 plus 2 times the cube root of 1 plus 2 times the cube root of 2 all the way down to 2 times the cube root of 7. And the last one's just going to be plus the cube root of 8. Now, it's a boring calculation when you're stuck doing it by hand, but computers are really well suited for this kind of repetitive, tedious operation. If you calculated this all out and add it all up, you get approximately 11.7296, which is pretty good. Now, how good is it? Well, the true value is 12. And you can calculate the true value just by using the fundamental theorem. So how did we do? What's the relative percent error? Can you guys calculate that? Remember how that one goes? Okay. It's nice if I had a calculator with some batteries. So let's calculate the relative percent error. Let's do a nice fractions for ourselves. So it's going to be 11.7296 minus the true value, which is 12, divided by 12, and then I'll multiply by 100. Now, some people take the absolute value of this, and maybe some people will do it true minus approximate. Doesn't matter. In this case, the negative value that we get reflects the fact that we had an underestimate of the true value. That's fine. The relative percent error is about 2.25%, so 2.25%. Not bad, not exactly great, but not bad. How are we looking with the trapezoid rule in this first one? So hopefully it's nothing really too onerous. What we're going to do is do this again with a different calculation. We're going to do Simpsons Rule. And then we'll practice Simpsons Rule again by hand. Okay, so how does Simpsons Rule differ from the Trapezoid Rule? Well, Simpsons Rule is really, really good. Let me see if I can't view slideshow from current slide. There we go. The difference with Simpsons Rule is that instead of using trapezoids in each of those subintervals. Now let's go back here. Yeah, right here. So we use a trapezoid to approximate the area here. With Simpsons Rule, what you do is you choose kind of a midpoint here and then fit a parabola here. You actually fit a parabola and then you integrate the parabola. And it has an advantage that's a little bit of a surprise if you study numerical analysis, that it's very accurate and can actually integrate things up to degree 3 polynomials completely accurately. Now you don't have to worry about that kind of stuff. Let's take a look at what the effect is on the formula. So when you're looking at the formula for Simpsons Rule, it's a little bit different. You're going to take the length of your interval, b minus a, divided by 3 times the number of points you use. But then, I don't know, can somebody describe to me the pattern of the functions that we're going to use here? We've got all these endpoints of our subintervals, but what's the pattern? What are you going to keep in mind when you evaluate these things at home or on an exam? Is there a pattern here at all? Yeah, so you get the endpoints, right? So f of x sub 0, another word for that is a. F of x sub n, that's your b. So the endpoints are just left alone, but in between, you're right, they alternate. 4, then 2, 4, then 2, etc. So it definitely has a pattern. And let's see if we can't follow through on that pattern as we try and repeat our analysis of the previous problem using Simpsons Rule. And this time I'm going to let you work it out. See what you get. So let me flip back here to Simpsons Rule. So in this case, it's going to be the area is approximately 8 minus 0 over 3 times 8 times f of 0 plus 4 times f of 1 plus 2 times f of 2. I'll actually write it all out. What would the next term be? Ben?
4f of 3.
Good. 4f of 3. Then 2f of 2. How about 2f of 4, sorry. 4f of 5 plus 2f of 6 plus 4f of 7 plus f of 8. Wow. So that's going to equal 1/3 times the cube root of 0. I'll do that one for you. I'll do the second one as well. 4 times the cube root of 1 plus 2 times the cube root of 2 plus 4 times the cube root of 3 plus 2 times the cube root of 4 plus 4 times the cube root of 5 plus 2 times the cube root of 6. Almost done. 4 times the cube root of 7 plus the cube root of 8. Alright, if you're stuck evaluating this by hand, it might be worth noting that, you can kind of bring some of these together, maybe factor it a little bit, or, it's up to you. But there is a little bit of a pattern here that would allow you to rearrange things. It's up to you. Just as a reminder, the cube root key is under the math menu. It's the 4th option down. So cube root of 1 I'll just do by hand. That's just 1. But then I have 4 times the cube root of 3 plus 4 times the cube root of 5. And then I also need the cube root of 7. So that's the total of all my odd cube roots. And then I'm going to multiply those by 4. Let's also total up the even cube roots. I need to multiply those by 2. So it's going to be 2 on the outside, 2 parentheses, cube root of 2, and the cube root of 4, and the cube root of 6. So it's not necessarily a fun operation. We got something like that. Last but not least, don't forget we need to multiply that total by 1/3. That's equivalently dividing by 3. So divide by 3. I'm thinking I must have made a mistake someplace.
Cube root of 8.
Oh, cube root of 8. Oh, okay. All right, so let's go back up here. And I'll add 2 for the cube root of 8. Now divide this by 3. It's looking a little bit better. Let's see what happens with our relative percent error. So I'll take this number and I'll just store it in x. We'll take x minus 12 divided by 12 and times by 100. So a lot better. We're only off by about 1.14% as opposed to 2.25% for the previous one. So, like I said, a lot better. Okay. Let's see, the total on that one was about 11.863. How are we looking on these first two? Pretty enthused? Okay, good deal. So 11.7 and 11.86. The nice thing about these is that you can apply these to situations where you don't necessarily have a function. If you just have some data, then you can do that as well. So this is data taken from a GPS during a bike ride, and it's taken at regularly spaced 5-minute intervals. There's your heart rate. Now let's think about what the area underneath this curve would represent. If you took the heart rate and plotted it out, found the area underneath this curve, what would it represent? Nick? Yeah, total amount of heartbeats. So how many times did the heartbeat for this athlete in this interval? Well, here's a good question for you. How many sub-intervals do I have from 0 to 40? Well, based on these. Well, there's 9 points. How many sub-intervals then? 8. 8. So 8. So n equals 8 sub-intervals. Remember, because the number of endpoints is one more than the number of sub-intervals. Well, even though we don't have a function, we can still try and find the area underneath this curve using Simpsons Rule. So let's do that. Let's work on that. So let's see. Area is going to equal, or at least approximately equal, let's see, it's going to be 40 minus 0 over 3 times 8. And then I'm going to want f of 0 plus 4 times f of what?
5.
F of 5. And then 2 times f of 10. All the way down to 4 times f of 35 plus f of 40. So you have some arithmetic in front of you. See if you can't work on that. I'll pause and give you a chance to give this one a try. First one with the right answer gets tickets on the 50-yard line to see the Lions this Thanksgiving Day. I don't see a lot of people working extra hard. We had to come up with something else, something actually meaningful. So if we write things out, this is just a long total. There's nothing other to do than grind it out. And I think we get, what, 3701 or something? Wait, 3661? 5/3 times what? 3661, yes. Yeah, so 6101.67. Now, of course, regarding the fact that this is heartbeats, then it probably makes sense to round this off to the nearest integer. So 6102. Yay. Okay, are you getting a feel for Trapezoid Rule and Simpsons Rule? Now, there are some error terms, some things you could say about the error in using these things. And it's not a whole lot that I want to say about this, but I do want to note something here for you. So let's take a look at the formulas for the error of Simpsons Rule and the Trapezoids Rule. So the worst that you're going to be using the trapezoid rule is the cube of the length of the interval divided by 12 times n squared. N is the number of points that you're using, or excuse me, the number of subintervals, I should say. Number of points is one more than that, times the maximum of the second derivative. Okay. So as this interval gets bigger, your error is going to get bigger. But what can control that? Well, what could make your error term smaller? Well, yeah, more subintervals. All right. This you're kind of stuck with. All right. There's not much we can do about that. But there's a nice little bonus in working with Simpsons Rule. Notice that not only is this bigger and we've got an n to the fourth, but here it's governed by the fourth derivative. So let's take a look at something real quick here regarding derivatives. Talk about polynomials. So let's take a look at p sub 3 of x, just a general cubic polynomial. Ax, yeah, I want cubed, plus bx squared plus cx plus d. And let's calculate the fourth derivative here. So, cubic p3 prime of x would be 3a x squared plus 2bx plus c. If I take a look at the second derivative, then I get 6a x plus 2b. What's the third derivative? Just 6a. And finally, what's the fourth derivative? Well, if this is a constant, what's the derivative of a constant? 0. So basically what this is saying is that if the error term that we're given for Simpsons Rule is correct, then this is perfectly accurate for finding the area underneath a cubic polynomial, which is strange because Simpsons Rule was created using a quadratic polynomial, but it still integrates perfectly if you're working with cubic polynomials. So kind of an interesting little side point here about Simpsons Rule, but it's perfectly accurate for cubic polynomials. It's a good rule. Now, they do a lot better. And the branch of mathematics that studies how to do these kinds of things is numerical analysis. It's like, all right, well, what do you do when you can't do things using the fundamental theorem and other things like that? So it's a cool branch of math. But for now, for homework, Try problems 1 through 5, 11, and 25. Good luck.